Hi, this is Felix from Nexema. Today I'm going to explain you why photo-induced hyperpolarization is more efficient at a low magnetic field. But first, if you still need to learn the basics of photo-induced hyperpolarization, also termed photo-CIDNP, I invite you to look at my former video where I explain all the basics on a relatively superficial level, so even if you are a beginner, this should be easy to understand. So to trigger photo-CIDNP, what you need is to have a photosensitizer that is present in your sample and you excite it using light. Your excited photosensitizer ends up in a triplet state eventually, and this triplet state photosensitizer can meet with a molecule M and eventually an electron transfer can happen. This electron transfer happens from the molecule, which gives an electron to the photosensitizer PS. And this results in the formation of a radical pair. And this radical pair is formed in the triplet state, meaning that the two electron spins are parallel. And when you have a triplet state, you cannot give back the electron from the photosensitizer PS to the molecule due to the Pauli exclusion principle. Consequence of that is your triplet state radical pair is a bottleneck. It cannot exchange back an electron to recombine into ground state products, and it cannot mix to become a single state radical pair, which will be allowed to recombine. And this is because you have an electron exchange term between the two electrons of each radical. So what happens is after a few nanoseconds, your radical pair diffuses apart. So each radical will diffuse apart in the bulk, and with the distance between the two radicals, the electron exchange term will vanish. While the two electron spins are coherent and in a triplet state in the beginning, they have different resonances in the magnetic field, B0, due to their different magnetic momentum, the G factors, so GPS and GM. In the rotating frame, this looks like they are dephasing. So when the two electron spins are in phase, they are in a triplet state, and when they are antiphase, they are in a singlet state. And we can have a look at it this way. The frequency at which they mix between triplet and singlet state depends on the difference between their two magnetic momentum, so the delta G, and the static magnetic field B0. The two radicals can meet after a time tau, and the probability for them to be in a singlet state depends on the frequency of singlet-triplet mixing, so omega st, times this delay tau. To understand why we have hyperpolarization, we need to consider the hyperfine coupling constants, HFCCs, and this is the interaction between the electron spin and the nuclear spin. So when you have a nuclear spin state for your molecule M that is beta, the hyperfine coupling constant, HFCC, will be of a value of minus 1/4 A. And when you have a nuclear spin state alpha, you will have an HFCC of a value plus 1/4 A. And those hyperfine couplings, they add up to the electron spin resonances of your molecule M. So in the case of a beta spin state, you will have minus 1/4 A. Okay, so we'll have a smaller resonance frequency for your electron. And in the case of an alpha nuclear spin state, the resonance frequency of your electron of the molecule M will be increased. This also affects the difference between the electron resonance frequencies of your photosensitizer and of your molecule. So in the case of a beta nuclear spin, you will have a smaller difference in electron spin resonances. And when you have a nuclear spin alpha, you have a greater difference between the electron spin resonances. So as we saw just before, this translates into slower singlet triplet mixing frequency in the case of a beta spin state. And in the case of an alpha nuclear spin state, this results in a higher frequency of singlet triplet mixing. So what we see is that when we go at time tau, we will have more singlet state in the case of nuclear spin state alpha than in the case of nuclear spin state beta. And this is what brings to the hyperpolarization. So you can only have the singlet state that will be observed by NMR. So you will have more alpha spin state than beta spin state at the end. And this is your hyperpolarization. Polarization. So let's reverse the scale and zoom a little bit into this moment tau when the two molecules meet again. And what we see is that for the beta state, okay, in yellow, we have less singlet state than for the alpha state, which is in purple. And the difference between the amount of singlet state that you have for each nuclear spin state is what will be the hyperpolarization. So you see it's tiny, but in NMR this is enough, right, to increase already the signal to noise. And let's now consider what happens when we change the magnetic field. So let's consider that we were at the 600 megahertz in proton resonance magnetic field, so that will be about 14 Tesla. And now let's see what happens when we reduce this magnetic field. And let's assume 60 megahertz, but of course this is not a scale, this is purely indicative. But what we see is that the difference between the two electron resonances changes due to the dependency on the magnetic field of the G factors, okay? But the hyperfine couplings are not magnetic field dependent. So what you see is that this dephasing will increase when you have a smaller difference between the two G factors. So they will dephase faster. So we can expect that we build hyperpolarization as well faster. Of course, here we don't really see that at time tau. It's very difficult to observe if we actually have some hyperpolarization, but indeed we have. And when we plot the two hyperpolarization curve corresponding to the difference between the singlet state population, we will see that this increases faster at 60 megahertz than at 600 megahertz. So we build more polarization at time tau. And this does not depend on how fast we mix singlet and triplet state mixing. What matters is how fast do we dephase the two electron spin resonances. All right, so let's quickly summarize. In photo-CIDNP, the radicals can go from a coherent triplet state towards a singlet state because of the difference of resonance between the electron spins of the photosynthesizer and of the molecules. But when we add the hyperfine coupling components, it will induce a difference into two cases. When you have a beta spin, you will have a slower mixing between singlet and triplet state than when you have an alpha spin. So the frequency of mixing between singlet and triplet state will depend on the difference of resonances due to the Zeeman interaction with the magnetic field and the hyperfine couplings, and depending on the nuclear spin state. The relative weight of the hyperfine coupling will be increased when you have a smaller magnetic field because the Zeeman interaction is much weaker, but the hyperfine coupling is not dependent on the magnetic field. So we can approximate this relationship with a very simple equation where the polarization, gamma, or the difference between the number of spin state alpha and beta, can be estimated by the ratio of the hyperfine coupling over the square root of the difference between the G factors times the magnetic field. So you see that when you reduce the magnetic field, you will have an increased yield in polarization, as we could see in this video. And this has diverse implications, not only into the signal to noise enhancement, but as well when we do fragment screening, like what we do at NextMR. I hope this video has been useful for you to understand why photo-induced hyperpolarization is more efficient at a low magnetic field. And we will see you next time with more videos about photo-CIDNP and its implication for life science, including for fragment screening.